Hello, everyone, and welcome. My name is Reachability, and today in this webinar, we're going to talk about how ARMO leverages cloud-native technologies to create continuous security. We will talk about three different security aspects. Two of the topics are Kubernetes native, where we will talk about Kubernetes native policies, and the third one will focus on the vulnerabilities that affect your security posture of your applications. And as we take our journey today, we are going to see how you can leverage your CI/CD to put in practice those aspects and improve your security. And I'll also show you how generating runtime policies based on application behavior during testing could reduce your attack surface. So this is a typical threat model for Kubernetes clusters. Most of the time, pods can be accessed from the public internet by a service or an ingress, thus allowing them to communicate with the outside world. Another path of attack can be through the software supply chain via the image registry. So the first thing we're going to examine is an exploit through the application, or in other words, your vulnerability posture through your applications. We will be looking at how you can reduce the noise coming from those vulnerability scans and help you focus on what really matters. We will also look at the attack path where attackers gained access to your workload and code execution permissions within your pod. In this case, the attacker has two options for lateral movement. They can either target your kernel and then try to escape the confinement of the containers and ultimately, of course, the pod. And these are called kernel exploits because if they are successful, they will enable the attackers to take over your cluster because every Kubernetes node has its node secret. And these are most simple files on the file system of the Kubernetes node. So once an attacker gets that, attackers are all set to talk with your Kube API server as a Kubernetes node, and of course, giving them a lot of freedom. Another way they may progress is from that pod is bilateral movement inside the network. So this is how they try to gain access to other pods or go after internal unprotected parts of the clusters. Parts of that, those parts are not exposed to the network, but they are exposed internally. So to recap the things we are going to talk about today is one, how you're going to reduce the noise around potential application exploits. Two, how to decrease the node attack surface. And three, how to decrease the attack surface for lateral movement. Combining these three, we'll show you how to effectively decrease the blast radius of a potential attack. So let's start with the application vulnerabilities. We all use different security scanners in our environments to find the vulnerabilities inside our software package in the container images. And there are many great tools out there, but most of them provide an output which is overwhelming and hard to handle, meaning you get a very big and long list of things to handle, and you're not sure where to start. And that's the noise. So the first step we're going to take is to use ARMO Platform's Reachability feature. And under the hood, ARMO Platform uses Kubescape, which is the CNCF sandbox project, and it's focused on Kubernetes security. And it installs an eBPF agent on every node, and this agent reports all the file activities on each workload running in the cluster. So the files that are touched inside the workload enable ARMO Platform to take the SBOM of that container image running inside that workload during runtime and cross-check with the files that are touched inside the container. And of course, mark the packages which were opened inside the container. And this enables the creation of a filtered list of packages that are reachable within the workload. And this shorter list of vulnerability reduces the noise and increases the signal. So let's see how users of ARMO Platform can lower the number of vulnerabilities to handle by 80% and more. So in this demo, I will show you the implementation of reachability in ARMO Platform. And as we discussed, this indicates if a vulnerability is even reachable based on whether it was loaded into memory or not. And let's illustrate this with an example. Let's say that my CISO is knocking on my door and is asking if we're exposed to a certain vulnerability. I can use the vulnerability section in ARMO Platform to look at my images, my workloads, to search for the specific vulnerability and check the reachability of it. Up at on the top, you can see the grand total of vulnerabilities on our cluster and their breakdown according to the CVSS severity score. But ARMO doesn't stop there. We can also filter according to different criteria to determine the severity and the priority of the vulnerability. And I want to look at this workload right here, which shows that I have many vulnerabilities to fix. And let's dive into this workload and examine the results for it. So I can see right away that this workload has 1,200 plus vulnerabilities. But if we look closely, we see that only 200 of them are truly reachable in my environment, meaning loaded into memory and therefore, of course, exploitable in this context. Let's clear all the filters right here so we can see the full list of the vulnerabilities. So we have that very, very long list of vulnerabilities. And I can use the filters to refine the results even more and get a list of the critical and high vulnerabilities that are also reachable and has a fix. And these are the ones that I should fix first. Now, I'm not saying you shouldn't be mitigating the other vulnerabilities or solving them, of course, but the ones I see after using these filters are the most dangerous vulnerabilities for this specific workload. So moving forward, we said that we're going to talk about kernel protection as well and shrink the attack surface on a Linux kernel inside the Kubernetes node. So in the pod security context, you can determine the user ID or the group ID of that container. And I just want to remind you that running your containers as root is not recommended. You also need to address the Linux kernel capabilities of the processes inside the container. So check that if you're giving a container the privileged container capabilities and if it really needs to be privileged. So I'll just mention this is typically off by default and you should be fine. The third element in kernel protection is seccomp profiles. They allow us to control what kind of system calls your containers are permitted to make to the kernel. The ARMO research team, he examined the CVEs for the Linux kernel, which were showing container escape, and found that most of the system calls they made were exotic system calls, usually made by applications that manage the node. And applications don't typically need these types of calls. So removing all unneeded system calls is another way we can protect our kernel, which underscores the importance of seccomp profiles, of course. And to apply seccomp profiles, we can use a pre-made list of system calls our application is allowed to make. And the risk here is that it might break our app and will require modifications. They are also likely to be over-permissive. So let's look at another way. Another approach is to create a manual definition of the seccomp profiles and create a manual list of system calls your workloads are allowed to make. You can imagine that this is a very tedious and error-prone task. So not to mention that there is knowledge gap here between the app developers' understanding and the needs of the DevOps engineers. And ARMO is offering a third option here, which is an auto-generated of a seccomp profile list based on actual application behavior. So a bit forward, I think that we could all agree about the importance of the network security and that locking down of unneeded network paths in the application environment. And if not, I'll just mention that the lack of proper network security may allow the attackers to carry out reconnaissance, lateral movement, extract data from pods through unprotected APIs, and more. So there is a major problem with network policies, not only in cloud native environments, but in general in cloud environments. In comparison with old school self-hosted monolith environments, cloud and cloud native have multi-microservice architecture, which means that many components, and it's hard to know who needs to talk to whom. So you can invest the time and map it manually, and after you apply it, you might break the application. So thus begins an iterative cycle of tweaking until everything, of course, comes to work together. So all of this can significantly slow down your deployments. Even if you did get it right, the next time the application changes, it may break again due to using a different network path or APIs. And since we work in an agile environment, that change may be only a week or two away. So maintaining network policy becomes a problem even bigger than creating the policy in the first place. And in any case, it's a lot of work. So ARMO just made it easier. Using the ARMO Platform's network policy generator, Kubescape maps your app using the same eBPF engine used for relevancy, for the reachability. Then ARMO creates a suggested network policy that is based on your current app's behavior. So it means that you get a generated network policy that won't break your app when applied. Another thing is that the network policy generator also suggests hardening options. So if ARMO Platform recognizes that the app is not using certain endpoints that are listed in the existing network policy, it will suggest a hardened version of that policy that you can apply inside your cluster. And let's see how it works in action. Okay, so I have a cluster right here on which I deployed several microservices like Argo CD, Prometheus, and some more. And this is a list of the workloads and the status of the network policy applied on them, if any, or the suggestion for the generated by ARMO Platform. So right now we are looking at Argo CD namespace, and we see all workloads already have a network policy applied to them. But ARMO Platform suggests a hardening for those network policies. So if we click right here, we see the suggested network policy generated by ARMO Platform for this specific workload. And it's, of course, based on the app's behavior. So it's not breaking your app. I can see the graph for the visual representation of the network policy recorded by ARMO Platform using Kubescape. And I can view the applied policy if it exists. It's coming alongside the suggested one that will, of course, further harden the workload. And from here, I can download the policy, and then I can apply it to my cluster and my workload. And I can also choose multiple workloads to download the policy for, and I will get all network policy manifests for those workloads. And in the demo and S namespace, we see there's a workload without any network policy applied. So right now I can use ARMO Platform suggestion to generate one based on the app's behavior that we see right here. You see the information that was recorded using Kubescape by ARMO Platform. And on the right side, on the right tab, we can see the network policy, the suggested network policy itself. So now we understand that Kubernetes security is multifaceted and has interdependencies with the containerized applications running on it. We also understand that there is a lot of toil associated with getting it right and keeping it that way. So now let's imagine a magic box where we can put our application and everything it needs in order to run. And the box produces a short and focused list of vulnerabilities, network policy suggestions based on your application's runtime behavior, and seccomp profiles. Isn't it great? So in this world of automation, security practitioners and DevOps engineers are happier and more focused on productive work rather than error-prone manual work that also slows them down. And this leads us to think that if we have a CI/CD process, we should have continuous security as well, because it's a great approach to hook all these existing processes in our CI/CD test that we are running anyway, right? So if we could capture all this information during the testing phase, we can turn these behaviors into policies and apply them to our environment to improve our security. So by this point, you are probably thinking, this is great. I need one of those, right? So while I'm not disputing this is indeed a game changer, not everything is perfect in life. And for the sake of full disclosure, I will highlight some of the problems. So all the features discussed earlier are heavily dependent on a data stream coming from the eBPF. And this requires an allocation of additional CPU sometimes to carry out the test that I just described earlier. And that has a monetary cost associated with it. And if there are missing test paths in the CI/CD, the resulting policy objects might break your application since the production application is using a different path. And if the system is incomplete when conducting the tests, it may lead to wrong policies since those need to be generated considering the production behavior of the application. And an approximation may not be good enough and ultimately break it. So as a result, the recordings of or information captures need to happen more to the right towards the CI. So now let's balance out the risks with the rewards. So you gain a massive improvement in your security posture, adding network micro-segmentation, adding seccomp profiles, increasing the signal to noise ratio of your vulnerability scans improves your security posture by an order of a magnitude. And you only need to set this up once and then monitor and tweak it. The endless iterative processes discussed earlier are now gone. And of course, it helps you put the concept of least privilege into action quickly and constantly. So I would like to thank you very much for joining the ARMO webinar. Feel free to try out ARMO Platform by going to armosec.io and signing up.